Now, when I was looking at the rest of the schedule, it turned out that no big deal, but we ended up missing a day last week because of a storm, well, non-storm, I guess. And so when I looked at the notes I have, the topics that remain are boundary value problems, chapter 13. And in the schedule, I had set aside 2 class periods, this week for section 13.1, and then 2 class periods for 13.2. And when I look at the notes that I have, I'm definitely going to get through all of these notes in one day. And the same is true for the other section. In other words, I think all new material I will have covered by the end of this week. After that, the only thing left to handle would apply if there's anyone among you who is planning to do the coding option for a final, which involves implementing methods for solving boundary value problems, or the oral option. Now, granted, you don't have all the information to make that choice yet, although some of you may have decided already. I'm aware of at least one who is for sure doing the oral option. Okay, is there anyone who is as of this moment, still open to doing the coding option? Or have you all decided like, no, I'm not gonna touch that? So, anyone? I want to know where anyone falls on that, even if it's still undecided.
I'll be that one.
What?
I'll be open to that.
Really?
Yeah.
I thought you were decided. Okay.
Yeah, but I'm still curious.
Okay, all right.
She just wants to hear what you have to say, I think.
Okay.
I'm open to recording.
You do?
Yeah.
Okay.
No, I'm not sure.
That's fine. That's an acceptable answer. Taylor?
I'm settled at work.
Oh, okay. All right, so we have some of each. So for anyone who is at least open to coding, then there'll be an extra class period to talk about like for hints and stuff. Okay. Right, now, but otherwise, that's it. Now, okay, so for my one last, yeah, make your choice and let me know. Whatever you do, no matter which option, Thursday, May 9th, I guess by 11:59 p.m., is when I really look to have everything in, because grades are due on the 13th. Won't have enough time for it all. Okay, so now let's get into the final topic. So we've seen ordinary differential equations for initial value problems. So now we have, so your solution in that case is a function of time. Now our solution is a function of x, one space dimension. So here's our problem now. We have a second order ODE, so y double prime is some function that may depend on x and also y and y prime. And this encompasses either linear or nonlinear ODEs. We will be looking at both. Your ODE is defined on some bounded interval, AB. A and B are both finite. And then you have, instead of initial conditions, you have boundary conditions. So at the endpoints, A and B, your solution is prescribed to have given values alpha and beta. Now, here's some assumptions that we're going to make that are at least sufficient to ensure a unique solution. They're not absolutely required. So first, f should be continuous in all of its variables, x, y, and y prime. the domain in consideration, that x can be an interval and y prime can be anything. The partial derivative of y, f with respect to y, should be positive on this domain. And also the partial f with respect to y prime should at least be bounded. So these are assumptions that are made in kind of like basically some kind of existence uniqueness theorem that would guarantee a mean exclusion. So we're going to look at two approaches, one today and one on Wednesday, for solving this kind of problem. And for the first one, of a shooting method, we're actually going to fall back on what we've already seen with solving ODEs from initial value problems. So what we do is we're going to transform this boundary value problem into an initial value problem. So same ODE, y double prime is equal to f, and we still have the same boundary condition at x equals a. So x equals a is serving as you think it's like as an initial condition. So you think of x equals a as the initial time, if you will. And then now when you solve the initial value problem involving a second order ODE, our time-stepping methods are designed for first order differential equations. So when you have a second order differential equation, the way you apply these time-stepping methods to it is you rewrite it as a first order system. So we have new variables, y1 and y2. Note I'm using superscripts. So I want to emphasize here, y superscript 1, y superscript 2, these are not exponents. I am not squaring a dang thing in any of this. So don't even go there. I'm not sure why I chose superscripts here. I must have had some compelling reasons for it. But anyway, so now, because anytime you have an ODE of order m, you can rewrite it as a system of m first order equations. And all those equations except the last one are trivial in that the derivative of each variable is one of the next variables. The derivative of your final variable, so y2 is y prime, that comes from your original ODE. And instead of saying f of x, y prime, we have f of x, y1, y2. So this is something you can always do. So when you have a system of two first order ODEs, like we have here, you must have two initial conditions. One of them is y1, that's the first left boundary condition for the original problem. And then we have the condition on the derivative becomes your second initial condition in your first order system. Now, the problem here is this value t is unknown. So the goal is to find the right value of t. Now the t is the value of a first derivative at x equals a. So it's like you're trying to find the right trajectory. So your solution is starting at the correct point, but is it moving from that point at the correct angle? So you're trying to aim. That's why it's called a shooting method. You're trying to find the right angle to fire. I just realized anyone online cannot see what I'm doing here. Taylor, I'm going to the motion of aiming a gun. So I probably shouldn't say that out loud in this building. Okay. So that the solution will be equal to beta at the other end. Okay, and that's where the term shooting method gets its name. I'm trying to find the right angle to fire, and that's indicated by t. So to our solution, y, which is equated to y1 here, at x equals b, for the value of t star, the value of t that we've chosen, if we have the right one, should be equal to beta. So you can think of this equation here is that we want some function, capital F of t, to be equal to 0. And t star is the root. Okay,
So we turn it into a root finding problem.
yes, that's exactly what we do, yeah. Okay. Now, the discussion for linear problems versus nonlinear problems is very different. It's um, right. Um, okay. It's a lot easier for a linear case. So when we have a linear boundary value problem, so for general, we have a function f of x, y, and y prime. But when it's linear in y and y prime, then we can just write it in this form. So what happens in this case is df dy is equal to q. So we're assuming that q is positive. And then df dy prime is just equal to p. Okay. And because p and q are functions of x, but they don't depend on y, that's what makes it a linear ODE. Okay. So here's how we can solve this very quickly in the linear case. We break it down to two problems. So for first we solve this problem with the same ODE and our left boundary condition, but then the derivative will be equal to 0. And a solution of that I'll call y1. So we just solve this by whatever means. And then for y2, the solution to this problem, where we leave out the r of x, so this ODE is homogeneous, we have a 0 initial value, and then the derivative value at the left end that will be equal to 1. So then the overall solution to the original problem will be equal to y1 plus a scaling factor t times y2. So then I look at y double prime, and I substitute this into the original ODE, and expressing y using this form, y1 plus ty2, what we find is that this solution y of x does satisfy the ODE. Because you can think of y1 as being like a particular solution, and y2 as being a homogeneous solution. So we can have any multiple homogeneous solution, it's still a solution of the original ODE. So things you learned in your introductory ODE class. Now, what about the boundary condition? Now, at the left boundary, we plug in x equals a. Now, y2 is equal to 0 at x equals a. So, any solution of this form automatically satisfies the boundary condition at the left boundary. Now, for the right boundary, the derivative value will be equal to t. But when we plug in x equals b, we have whatever y1 of b is, plus t times y2 of b. And we want this expression to be equal to beta. But y1 of b and y2 of b are now known once we solve these two problems. So we can just take this equation and trivially solve it for t. And then we have our derivative value. So then, once we solve for t here, for this equation, and substitute it back up in here, then we have a solution of our overall problem. So yes, we did have to describe this as a root finding method problem. But normally when you're trying to find a root of the function, you carry out iteration if a function is nonlinear. The function, like if you describe it as a root finding function involving a function f, like this kind of function here, the equation for t ends up being a linear equation so trivially solved. So like there's really nothing to do here. It's not very interesting. It's not even a numerical analysis problem, really. Okay. So that's an example. So here we have our ODE. So this part here is our R of x. P is equal to 2 and Q is equal to -1. We have these boundary conditions, so 0 at 0 and -4 at x equals 2. So then we solve this problem where we inherit the left boundary condition here, and then the derivative is a 0 at x equals 0. And so this can be solved using like method of undetermined coefficients or variation of parameters, and you get this solution here. And then we solve this ODE that comes from this one where we drop the source term, the R of x part. At x equals 0, it's 0. The derivative at x equals 0 is 1. And then we get this for our solution of the second problem. Now we have a y1 and y2. So then our solution, our general solution, is y1 plus t times y2. So then we plug in x equal 2 in here, and y1 of 2 turns out to be, like if you plug in x equal 2 in here, you end up with 4/3 e squared minus 4. And then you plug in x equal 2 here, and you get 2e squared. So you take all this, and you set that equal to -4. And you can solve for t, and you end up with t is equal to -2/3. So then you can take this t value and substitute it in here, really just over here. And then you have your solution. So not a whole lot of numerical analysis going on here. In fact, for this particular example, there isn't any. But don't worry, that'll come. So any questions about how this example unfolds? But I should mention, if you have a problem like this one, some linear, second order linear ODE boundary conditions. Now, in an introductory ODE class, you're taught two methods for solving this kind of problem. When you have this non-zero R of x here, because you take the like if the coefficients P and Q are constant, that's when you can use the methods taught in a class like that. Method of undetermined coefficients and variation of parameters. Now, there are significant limitations to both methods. Method of undetermined coefficients requires that the coefficients P and Q are constant. It also requires that R of x is of a certain form. So if it fits those conditions, okay, you're good to go. Variation of parameters is a little more flexible. It does not require the coefficients to be constant, but there are two significant issues. One is, if the coefficients are not constant, how do you find your homogeneous solution? You don't know. I mean, you can look through an ODE textbook from cover to cover to not find any answer to that. Also, even if they are constant, your R of x, you're right, your source term does not have to be of any particular form. The solutions expressed using integrals. What if you can't evaluate the integrals? Maybe you can use a numerical method for evaluating those integrals, which is kind of close to what we're practice doing. So I have an honor student who's working with these kind of problems, and what she's doing is interpolating that R of x locally by a quadratic, and that makes so the approximation, but it could be handled more easily that way. So these methods that you learn in OE class, sure, they're great for the narrow categories of problems for which they're designed. But outside of the category, they're like, I don't know. So, and that's why we have numerical weapons. Okay. Um, again, because I'm not making any assumptions beyond what I've already stated on the coefficients of PQR. Certainly not requiring either constant or any nice form. So now, where things get more interesting, nonlinear problems. So we still convert to a system of two first order ODEs, and we have an initial value problem. So we have a condition on y and y prime at the left boundary. So this function right here is going to be a nonlinear function now. And so we have to use some root finding method like Newton's method or secant method. Now I'm going to show Newton's method. Newton's method is actually the most complicated choice. Because I mean, it's also most appealing in terms of convergence. It is the most rapidly converging method of the ones we studied. But it's more complicated because it requires the derivative of a function you're finding the root of. So now, this function here, we're taking the derivative, partial derivative of this function with respect to its parameter t. Now, for convenience, I'm going to call that derivative of y1 and then call that z1. So here is our system of first order ODEs that is now nonlinear. So this first equation just said that the derivative of y is with y prime, and then here we have y prime prime, which is y double prime, is equal to f. So now I can find two new variables, z1 and z2, to be the derivatives of y1 and y2 with respect to t. What we get is since differentiation refers, because here, this differentiation, the prime, is differentiation with respect to x. And then we have differentiation with respect to t separately. But remember, partial differentiation with respect to two different variables, the order can be interchanged. I mean, yes, there's some continuity assumptions, which we're not going to burden ourselves here with. So we're going to assume things are sufficiently continuous. So the derivative of z1 so z1 is derivative of y with respect to t. z1 prime is the derivative of z1 with respect to x. So by interchanging order derivatives, the derivative of z1 with respect to x is just z2. So we're interchanging order differentiation of with respect to x versus with respect to t. Now what about z2? So here we have derivative of y2 with respect to t, and then we're taking derivative of that with respect to x. Again, by interchanging order of differentiation, that amounts to taking the derivative of this whole expression with respect to t. So what we have is, now, x does not depend on t at all. But y1 and y2 most certainly do depend on t. So what we have is partial of f with respect to y times partial of y with respect to t. But y is y1, and the partial derivative of that with respect to t is z1. So that leads to the z1 factor here. Plus, continuing the chain rule, partial of f with respect to y prime times derivative of y2 with respect to t. But that's z2. So really, all this is just a chain rule exercise. So now we have a system of 4 first order ODEs. So for y and y prime, and then z1 and z2 with derivatives of y and y prime with respect to t. Any questions about how these additional ODEs came about? Relatively harmless calculus. Now, we're about to solve a system of 4 ODEs, 4 unknowns. We also need 4 initial conditions. Right now, we only have 2. Y1's initial value is alpha. Y2's initial value is t, our unknown. Okay, that's given right here. So now we take the derivative, differentiating all of this with respect to t. So again, interchanging order differentiation. So derivative of alpha with respect to t would be 0 because alpha is just a constant. And then we take the derivative of t with respect to t, and that's going to give us 1. So those will be initial conditions for z1 and z2. So now I can show you the overall algorithm. Oops. In this case, here it is. So shooting method using Newton's method for the root finding part. So what we do is we choose the initial guess, T0, for our root finding iteration. We choose to have a grid spacing for our interval AB, equally spaced points. It's b minus a over n plus 1, so we're going to have n interior points, and then you also have a boundary points at x equals a and x equals b. So this outer loop handles Newton's method. So it's going to so each iteration of outer loop is going to carry out 1 step of Newton's method, but that 1 step is going to take a lot of work because the function that you're trying to find the root of involves solving an ODE. So we set our initial conditions based on how I just showed you in the notes. Now this inner loop carries out the time stepping. Now the time stepping, that we keep simple. We're just going to use Euler's method, forward Euler, to solve these ODEs. So we have so all we're doing is new value is equal to previous value plus h is playing the role. It's playing the role of a time step, even though this really is the spatial spacing. And then here we have h times the derivatives from all of our 4 ODEs. So basically, you can pretty much read off the 4 ODEs that we have here, and these derivatives on the left side with respect to x are replaced by forward difference quotients, and that's what leads to Euler's method. But that's Euler's method. So we carry out all of this. We think of it as time stepping, but our variable is x, and we make it all the way to the end. So once we reach the end of this inner loop, then our endpoint values are the values of our various functions at x equals b. So y1, that's our solution that we're looking for. And by taking the n plus first element, that's the value of x equals b. That's what we want to be equal to beta. So this part in parentheses, get every Newton's method formula. New value equals old value minus function value divided by derivative value. So the part here in parentheses is the function value, the function we want to be 0. We want the y at x equals b to equal beta. And then we divide by the derivative of this with respect to t, but that's why we're computing these z's here. So z1 also evaluated at the right endpoint x equals b. So this line right here, that's the Newton step. So that gives us a new t value to use for the next iteration. So questions about how we algorithm? Yes.
Okay. So you're using Newton's method because of that equation. So you're trying to find that value of t.
Yeah.
The equation you turn it into a root finding problem where the problem is non-linear, and that's why you have to use some iterative method.
Yeah.
That's how we end up using Newton's method because it's converging quadratically.
Yeah.
And that's what we want.
Yeah.
Now, I feel like in this algorithm, I'm seeing only Newton's method, like overall, like not okay. Where's Euler's method here?
That's the inner loop.
Okay.
Yeah. New value equals previous value plus step times derivative value.
Yes.
Yeah, from these 4 ODEs.
So you end up solving for that system of 4 ODEs for every single iteration.
Yes. Because you're doing it with a different t value.
Yes.
Okay. Yeah, so using Euler method on the entire variable is needed just to evaluate the functions we need for Newton's method. So when you say you always use Newton's method, well, yeah, this is all Newton's method. It's just with a very expensive evaluation. This approach is used in this example for this problem right here. And here's some MATLAB code that sets up the problem. So I define f at df2y and df2y prime as function handles, functions of x, y, and y prime, based on, so here we have y cubed minus y times y prime, so that's what I have here. And I'm using the dot star and dot exponentiate because I want to allow for the possibility that y and yp can be vectors. So just covering my bases there, it doesn't hurt to use the term. And then I take the derivative of this with respect to y. That would be 3y squared and then minus y prime. And then a derivative of this with respect to y prime, well, this would give me 0. And then this term is linear in y prime, so I would just have minus y. So this describes the problem. And then I set my boundary conditions, here my a and b, 1 and 2. And then my boundary values, alpha and beta. I choose a number of interior grid points, just choosing 10. And then this function right here, okay, this function is not shown, the code for it, because it's what you do as part of your final if you do the coding option. But at least you see how it's called, with the description of the problem, ODE, the boundary conditions. And then the last argument is an error tolerance. So we want to check for convergence as we compute these t's. Like if the difference between successive t values is less than some tolerance, then we can say that the loop will exit at that point. The exact solution to this problem, just worked out separately, turns out to be 1 over x plus 1. So then I go ahead and plot the exact solution in blue, curve in circles, and then plot the approximate solution, red dashes. And then this is the graph that is produced. Unfortunately, the publisher will not let me have color figures, so everything's in black and white. The solid curve is the approximate solution. Oh wait, these labels are backwards. Yeah, I think it's on my list of mistakes. Yeah, the solid line is the exact solution. The dashed line is the approximate solution. We see that they agree at the boundaries. There's a little bit of discrepancy in here, but we're only using 10 grid points. And considering the small number of grid points, to have it that accurate is pretty good. As the number of grid points increases, then these solutions will agree more closely. For those of you doing the coding option, I put some, I just posted in Canvas that assignment. And it's been on the assignments page in Canvas all along, but now I have a link from the main page. I have the starting points for the various M files involved. So there's some comments in there that give you an idea of how to get started. Okay. Questions about Newton's method or shooting method done with Newton's method? Let's get anyone off a coding option. I should mention that since Newton's method, for whatever function trying to find a derivative requires a derivative, it makes the shooting method here unduly complicated. Like if I was using, if I would solve this equation, but not using Newton's method, say I was using the secant method that doesn't require a derivative, then I don't need these equations down here. I would just be solving this system of ODEs, only two. Now it would not converge as rapidly because it's not Newton's method, but it seems like it would be worthwhile from an efficiency standpoint to stick with the slightly slower converging method and only have to solve 2 ODEs instead of 4. So I kind of went for the hardest thing in showing this. And I think it's one of the problems to put on the final, because you implement shoot do, right? So shooting method, Newton's method, and then you also with secant method, and it turned out to be simpler. Okay. I couldn't get the notes. Wow, I couldn't get the notes. So, now, so there's 2 key components here. What root finding method do you use? And also, what time stepping method do you use? So I just made a specific choice, can use method for whatever. So I use the hardest choice for root finding method and simplest choice for time stepping method. I could have done something like using the secant method and then using like 4-quarter Runge-Kutta for the time stepping part. So then this code in between would have been a lot more complicated. But there's 2 things you're wanting to converge. Like what happens is here, this example shows if you can get convergence for t, that you get the correct boundary value, but then you see that there's some noticeable error in the interior of the interval. So if you use a more sophisticated time stepping method like 4-quarter Runge-Kutta, then you're going to get more favorable convergence in the interior. You'll get more accuracy that way. And then whatever choice of root finding method you make would affect the speed of convergence on satisfying the boundary conditions. So you want to use something that's going to be methods are going to be effective for both. Now, if you use a decent root finding method, you're going to get convergence. So you can be assured that your right boundary condition will be satisfied to whatever accuracy you want. But then you really should use more accurate time stepping method in between to ensure similar accuracy in the interior, which I think it's safe to say, based on this plot here, we did not get. But that's a choice I made for Euler's method because I didn't want code that's a zillion miles long. So, and you could use a multi-step method maybe, but yes. But you need something for starting values, etc. Okay, so but this is just one approach because you think, okay, I've learned so much about how to solve initial value problems for ODEs, and if I'm able to use that knowledge for a very different problem, why not? But on Wednesday, we'll forget about initial value problems. How do we approach this kind of boundary value problem in a more direct way? That's what leads to finite differences. So iteration will still be important, like with Newton's method, but used in a very different way. That's where I previously covered how to solve a system of nonlinear equations for a root in higher dimensions. And so So those techniques are gonna become relevant to us now on Wednesday. Okay. So, we come to the end. How much left? Questions about anything? Homework? I know I'm behind on grading, I've had a lot going on lately, and people keep telling me stuff on me. But I promise I will get to my grading pretty soon, like I'm hoping within the next week or so, or like this week. Yeah. I guess that'll do it.
I have a question
Oh.
that I sent you earlier. I saw it.
Oh, when did you send that to me?
It was a while ago, but it was you responded, I just
Oh.
still didn't